Okay, so now we're going to see how we can use that solubility table to write different types of equations. And we'll start off with the type of equation we've used all along so far, which are known as molecular equations. Okay, molecular equations, we would say these are the typical types of equations we've seen before, where we represent the chemical formulas as they exist in solution as either molecules or formula units. So for example, I have sodium sulfate reacting with barium hydroxide to give sodium hydroxide and barium sulfate, and then I have my two here to balance our equation. I have my state symbols in there as well. All right. So in this type of an example of this equation, what we see here is that this is an example of what's known as a double replacement or a metathesis equation. So I have my general form for this. So generally, we can say if I have an ionic compound AD reacting with another ionic compound CD, what can happen is I can have two cations that swap their partners, that swap their anions to make two new combinations. So for example, the A and the C here, they can swap places with each other and make a new combination now. Now I make AD, and then I make CB, right? So this is an example of a double replacement or metathesis reaction. So in this specific example, the sodium and the barium are the things that swap places with each other. The barium ends up with this, like the barium starts off with the hydroxide. The sodium starts off with the sulfate. The sodium swaps places with the barium to end up with the hydroxide at the end. And the barium takes the place of the sodium, and the barium ends up with the sulfate. Right, so you have things that are swapping places with each other. That's a double replacement or metathesis. So we can represent that reaction using our normal molecular equation. What is actually happening on a particulate level? Well, we can come up with what's known as an ionic equation, which is a much truer representation of what's occurring in aqueous solution, because we just said, we spent a lot of time talking about this already, that in an aqueous solution, we actually have, for your soluble ionic compounds, you actually have ions present in solution. So in order to determine an ionic equation, what we need to do to write your ionic equation, first of all, we need the ions that are present. Okay, so any soluble ionic compound will actually exist as ions. Okay, and how do we tell that something is soluble? Well, it's going to have that AQ after it, but also we can use a solubility table. Any compound that is insoluble so that will be represented, or we can tell that because there's going to be a solid next to it. We can use a solubility table. Okay, it's going to remain as an undissociated compound. We're not going to break it into its ions because it doesn't dissolve. Okay, so if I take a look at each of these, I have my sodium sulfate, right? That is made up of two sodium ions and I have a sulfate ion. They're both aqueous. In my barium hydroxide, I have a barium ion and I have two hydroxides, so barium and two hydroxides. In my sodium hydroxide over here, I have a sodium and I have a hydroxide, but I have two of each of these. And then in my the barium sulfate, right, that's a solid. Okay, so that means we're going to keep the BaSO4 together. We're not going to split it apart. And that's the key thing when you write your ionic equations, right? So all we're doing then is taking each of these aqueous substances and we're breaking it apart into its component ions. So for example, the sodium sulfate actually is made up of these two things, a sodium and a sulfate. The barium hydroxide, this thing is actually made up of barium and two hydroxides. The sodium hydroxide, this thing is made up of two sodiums and two hydroxides. And then the barium sulfate, well, that's a solid. Okay, we're going to keep that together. That is not going to break into ions. We're going to keep that as it is. So identifying the ions is critical to doing this. When you write that out, this is called a complete ionic equation. What we can do after we have that complete ionic equation, we can take it and we can observe what does not change from the left side to the right side. In other words, are there species, put that in quotations, that are the same on both sides of the equation? And if there are, what we can do is we can cancel those. We can cancel them out because they don't change, right? They are the same. They're there at the beginning and they're there at the end. So we refer to those as spectator ions. They're just looking, they're observing, they're spectating what's going on in the solution. So for example, in the one that we just looked at up here, on the left side of my equation, I have 2 Na plus. And on the right side, I also have 2 Na plus, right? So it's the same on the left, same on the right. That's a spectator ion. I also have 2 hydroxides on the right side. I have 2 hydroxides on the left. That is a spectator ion as well, because it's the same on the left side and the right side. I can cancel those out, and we can cancel out our spectator ions. And what you're left with is the actual reaction that is occurring. And the actual reaction that is occurring here is the sulfate and the barium ions are combining together to make the barium sulfate solid. And what we end up with when we write those out, that is then known as the net ionic equation. Right, if you were to zoom in with a very powerful microscope, the formation of the solid, that is actually the driving force for this reaction. And again, the solid here that's formed, that's your precipitate, right, in this precipitation reaction. So you start off with your, let's go up here, to your molecular equation. There are typical types of equations. You want to make sure that these are balanced. So double check that it is balanced. That's key. Then we're going to split apart each of the things that is aqueous into their respective ions. That's your complete ionic equation. Then we will cancel out the ions that are the same on both sides of the equation. Those are your spectator ions. So spectator ions are canceled out. Then what you're left with is known as the net ionic equation, and that is the driving force for this reaction. Okay, so those are the steps here that are listed out. Let's take a look at an example of this. So it says, write the molecular ionic net ionic equation for the reaction between aqueous solutions of lead acetate and calcium chloride when we combine these. Okay, so we're going to write out the formulas. So you have PbC2H3O2 twice, reacting with calcium chloride, CaCl2. Okay, and then we can confirm from our solubility table that anything with the acetate in it is going to be soluble. So this is going to be AQ. All chlorides are going to be soluble generally, and potassium is not one of the exceptions, so that's also going to be AQ. I need to predict the products now of this reaction. Okay, and this, I have two ionic compounds. Okay, I can make a fairly safe guess that this is going to be a double replacement reaction. So the calcium and the lead are going to swap places with each other. Okay, so the lead then is going to take the place of the calcium to make lead 2 chloride. So PbCl2. Okay, and then I'm also going to make the other product here. The calcium takes the place of the lead to make calcium acetate. So CaC2H3O2. I want to make sure that I have my formulas correct because I want to balance out the charges, right? Like you've done multiple times before. And then I can use the solubility table to determine now which of these products is going to be my precipitate. So I have lead chloride, I have calcium acetate. Anything with acetate in it is going to be soluble. That's going to be AQ. Chlorides are generally soluble, with the exception of when chloride is combined with lead, and that is actually going to be my precipitate. Okay, and I just sort of glossed over how we use the table. Let's go back up and just confirm that. All right, so here we have up here, so we have our acetate ion, right? So anything with acetate in it is going to be soluble, no exceptions. Okay, and then we had our other product that we have with our chlorides. The chlorides are generally soluble, except when they're combined with silver, mercury, or lead. Lead chloride is one of the products, and that's why that's our precipitate here at the end. Okay, so we have our equation written out. You want to make sure that this is balanced properly. So let's see. We have one lead on the left, one lead on the right. 2 acetates on the left, 2 acetates on the right. 1 calcium on the left, 1 calcium on the right. 2 chlorides on the left, 2 on the right. Okay, so that's our balanced equation. Everything that is AQ, I'm going to split apart into its ions, right? So here, this is made up of 2B, 2 plus, AQ. Then I have 2 acetates, so I have 2 C2H3O2 minus AQ. Okay, so the lead acetate gives me those ions. The calcium chloride, this is going to give me calcium ion, Ca2 plus, AQ. I'm also going to get 2 chlorides, so 2 Cl minuses, AQ. Okay, my lead, the lead 2 chloride, that's a solid. Okay, so that is not going to break apart. That's going to stay the same because it's insoluble. So PbCl2S, that stays the same. And then my other product here, the calcium acetate, AQ. I'm going to split that into its ions. We have the calcium ion, Ca2 plus, AQ. And then I also get 2 acetates. That's the other ions. 2 C2H3, 2 minus, AQ. Right, so this here is my complete ionic equation. My spectator ions now, I'm going to highlight those. So what are the things that are the same on both sides? Well, I have 2 acetates on the left. I have 2 acetates on the right. Right, so that's a spectator. The acetates are spectator ions. I can cancel those out. What else? The same on the left and the right. Well, I also have calcium. Calcium, 1 calcium on the left and another calcium on the right. So those are spectator ions. I can cancel those out as well. So we can cancel out spectator ions, which in this case are the Ca2 plus and the 2 acetates ions. And what we're left with then is the net ionic equation. Where we just write out what remains. Well, what remains is I have like Pb2 plus, AQ, on the left side, combining with 2Cl minuses on the left side. It's the only thing left over on the left. On the right side, I have my PbCl2 solid. Okay, and that is the net ionic equation. If you were to zoom in on a with really powerful microscope, you'll actually see the lead ion, the chloride ion combining together to make that precipitate, that solid that comes out of the solution. It makes it cloudy. It has a yellow. This one will have a yellowish, orangish color associated with it. So that's the step-by-step systematic way to determine the net ionic equation. And by doing that, we can identify the spectator ions in the solution as well. There is a shortcut you can use to help you determine net ionic equations. Okay, and you probably may have figured it out from the two examples that we did. Okay, so the shortcut here is if you have, and you have to start with your complete. This is your molecular equation. Okay, so from molecular equation, identify the insoluble substance. Okay, so in this case, it's the lead chloride. So I have that on the right side. And all I need to do is to identify, well, what ions are found in it, or make it, what ions make up the insoluble substance. Okay, so in order to make lead-2 chloride, I need a lead-2 ion, and I also need fluoride, but I need two of them. And I'm just going to insert the aqueous in front of each of these. That's your net ionic equation. Right? That's a shortcut. If you don't want to go through, writing out the complete ionic equation, canceling out the spectator ions, you can get there fairly quick. Now, if the question is asking you just for the net ionic, you can use a shortcut. If it's asking you to write out the complete ionic, then you actually have to go through all the steps.